3 articles went up on a small publishing site. Call it Ink Post. All 3 were live. You could open them in a browser and read them. And for 3 weeks, none of them existed as far as the site's own search box was concerned. Type the title in, get nothing back. Here is the part that should worry you. Nobody got an error. No exception was thrown. No alert fired. The dashboard that counts failures sat at 0 the whole time. And that 0 was the bad news, not the good news. Nothing was broken loudly enough for anyone to notice. So let me show you exactly how that happens, why the 2 obvious fixes do not fix it, and what actually does. Here is the code, and it is about as ordinary as code gets. When someone publishes an article, we do 2 things. First, we save the article row in the database, inside a transaction. A transaction is a promise. Everything inside it lands, or none of it does. Then, once that promise has been kept, we push the article to the search index so people can find it. Now, read it again and look at where the transaction actually ends. It ends after line 3. The second write, the one that puts the article into the search index, happens outside it. 2 writes, 2 different systems. Only one of them is protected. So what happens if the program stops running in between? Not crashes, politely, stops. The container gets evicted in the middle of a deploy. The kernel kills the process because the machine ran out of memory. The node is drained. That gap between the 2 lines is a couple of milliseconds wide, and if you publish enough, something eventually lands in it. Now, the obvious instinct is to wrap it in a try and an accept and catch the failure. That does not work here, and it is worth being precise about why. An accept block is code. Code needs a living process to run in. If the process was killed, nothing ran. There was no exception because there was nobody left to raise it to. The gap is not a missing error handler. The gap is structural. So the article is durably in the database. The index call simply never happened, and the request returned 200 OK because the first write succeeded. The author refreshes the page and sees their article, live. Every dashboard stays green. 3 articles, 21 days, 0 alerts. This failure has a name, and naming it is most of the fight. It is the dual write problem. Anytime you write to 2 systems with no single transaction covering both, you have it. It is not a bug in your code. It is a missing guarantee. First instinct fix. Fix the second write. If indexing fails, wait a moment and try it again. And to be fair, this genuinely helps. If the search index was briefly down or slow, a retry gets you through. What it cannot do is close the gap. Look at where the retry loop lives. It lives inside the same process. It is the same code, in the same memory, on the same machine. If that machine goes away between the commit and the first attempt, the retry loop goes away with it. You have made the window narrower. Narrower is not closed. A window 1 millisecond wide still gets hit, just less often, which mostly means it is harder to reproduce.
Second instinct fix, and this is the one that real systems actually ship. A nightly job. Every night at 3 in the morning, rescan every article, compare it against the search index, and index anything missing. I want to be fair to this one because it works. It really does close the loop. And if you have this problem right now, it is a reasonable thing to do today. But look at what you have agreed to. You have agreed that your data is allowed to be wrong until morning. You have made drift a normal operating condition instead of an emergency. And notice the hidden condition that makes it safe at all. Indexing the same article twice is harmless. Re-indexing is repeatable. Charging a customer twice is not. Sending an email twice is not. So the patch does not generalize.
Now the actual fix and the shape of it is the interesting part. Because it does not retry the second write, it refuses to do 2 writes at all. Here is the move. Instead of performing the side effect, you write down that you owe it in the same transaction as the business data. So when someone publishes an article, you insert the article row, and you insert a second row that says, this article still needs to be indexed. Both rows go into the same database. Both are covered by the same commit. That is the whole idea. You have turned a promise you cannot keep, two systems and one transaction, into a promise you can keep. Two rows, one system, one transaction. The table those rows go into is called an outbox. In code, it is almost boring, and that is the point. One transaction, two inserts, one commit. The second insert is not doing the work. It is recording that the work is owed, along with enough information to do it later. What happened, and to which article. And now think about the crash again. If the process dies before the commit, neither row exists. The article was never published, so nothing is inconsistent. If the process dies after the commit, both rows exist. The article is published, and the fact that it still needs indexing is written down, durably, in the database. There is no in-between state where one is true and the other one is lost.
Now, the beat that almost every explanation of this pattern skips, and it is the one that will actually bite you. Look at these two versions side by side. On the left, the transaction commits, and then we insert the outbox row. On the right, both inserts happen inside the transaction, and then it commits. That looks like a formatting difference. It is not. The version on the left is the same bug you just spent 5 minutes learning about, one level down. Think it through. The transaction commits, the article is durably saved. Then, before the outbox insert runs, the process dies. Now you have an article in the database and nothing, anywhere, recording that it needs to be indexed, which is exactly where you started. You have added a table and a background worker and a whole pattern with a name, and you have kept the original defect. So the rule is short. If the write that records your intent is not inside the same commit as the data, you do not have an outbox. You have a dual write with extra steps.
So the rows are safe. Something still has to do the actual work. That something is usually called a relay. It is an ordinary background loop, and it is boring on purpose. Read a batch of rows from the outbox table that are not done yet. For each one, do the real side effect, call the search index. Then mark the row as done. That is the entire job. The relay is the only thing that talks to the outside system, and it is separate from the request the user is waiting on. So if the search index is down for an hour, publishing still works. The rows just sit in the table until the relay can drain them.
Now watch what falls out of this for free, whether you wanted it or not. The relay reads a row. It calls the search index. The index accepts it. And then, before the relay can mark that row as done, the relay dies. The row is still sitting there, still not done. So the next relay picks it up and indexes the same article a second time. You cannot engineer this away. It is not a flaw in the design. It is the design. There is no ordering of those two steps that is safe. Mark it done first, and you can lose the work entirely. Do the work first, and you can repeat it. You get to choose which one, and losing work is the worse of the two. So here is the honest statement. Delivery is at least once. Exactly once delivery does not exist. What does exist is doing the work once, and that is a different problem, solved on the other end.
That other end is the consumer, and the property you need there is called idempotency. In plain words, doing it twice has the same effect as doing it once. The way you get it is a key. Every outbox row carries an identifier that is stable, so the same event always has the same key. The consumer records that key when it processes the event, and crucially, it records it in a way the database itself refuses to duplicate. Insert, on conflict, do nothing. If the key is already there, the second attempt does nothing at all, and the database enforces that, not your code. Compare that with a plain insert. A plain insert happily writes the row a second time, and now you have two of whatever it was. And there is an ordering rule here that matters enormously for anything the outside world can see. If the side effect is an email or a charge, the check goes before the effect, never after. Claim the key first, then send. If you send first and record second, you have just rebuilt the crash window on the one operation where a duplicate is expensive. There is one more piece, and it is the one that makes all of this calm instead of tense: a reconciliation loop, sometimes called a sweeper or anti-entropy. It periodically compares the two systems and repairs the difference, which sounds exactly like the nightly cron I told you was a symptom. So what changed? What changed is that it is now safe. Earlier, the nightly backfill was load-bearing. It was the only thing standing between you and permanent silent drift. Now it is a safety net underneath a mechanism that already works, and it can run as often as you like, because the consumers are idempotent. Reprocessing costs nothing. Those two ideas hold each other up. Idempotency is what makes reconciliation safe to run. Reconciliation is what catches whatever the relay still misses. Neither one is enough on its own. And now the part most explanations leave out entirely: when not to build any of this. The outbox is not free. It is a table, a background worker, a retry policy, a way to see stuck rows, and a new class of thing that can wake you up at 2 in the morning. If you have one service publishing a handful of times a day, and the second write is something cheap and repeatable like a search index, then you probably do not want any of this. Write a small script that does the steps in order, log what it did, and check it. That is a real answer, not a lazy one. The outbox earns its keep when the side effects are many, or remote, or genuinely expensive to lose. Payments, emails to real people, events other teams depend on. So the test is not whether you can lose a write. The test is what it costs you when you do. If the honest answer is, we re-index it in the morning, write the script. If the honest answer is, we charged someone and never shipped anything, build the outbox. If that made the pattern click, hit like and subscribe. One concept all the way down to the code every time. And here is the vocabulary, so you can go and read further under the right names. The dual write problem, the transactional outbox, the idempotent consumer, reconciliation, sometimes called anti-entropy, and orchestration versus choreography, which is the argument about who is in charge of the sequence. If you want the long version in print, Chris Richardson, Microservices Patterns, Chapters 3 and 4, and Martin Kleppman, Designing Data-Intensive Applications, Chapter 11.